Now in linear algebra, we don't say perpendicular so much, we say orthogonal. We're going to define the notion of orthogonal so that the Pythagorean theorem is true. Let u and v be any vectors. Their lengths are norm of u and norm of v. And we draw the corresponding arrows. The arrow for u, the arrow for v, and the arrow for the sum u plus v. Now, so far, we haven't required that this triangle be a right triangle. So, in fact, this is not formally a hypotenuse. Now, the squared length of the vector u plus v is norm of u plus v squared, which is, by definition of norm, the inner product of u plus v with u plus v. Now we use some of the properties of inner product. By linearity of the inner product, we can break this up as the inner product of u with u plus v plus the inner product of v with u plus v. We can further break that up as the inner product of u with u, u with v, v with u, and v with v. Now, the inner product of u with u is the norm of u squared. The inner product of v with v is the norm of v squared. And these two terms are really the same by symmetry. Combining them, we get 2 times the inner product of u with v. Now, this last expression is equal to norm of u squared plus norm of v squared if and only if this term is 0. We want the norm squared of u plus v to be equal to the norm squared of u plus the norm squared of v if and only if the vectors u and v are orthogonal. So we'll define orthogonality in this way. We define the two vectors to be orthogonal if the inner product equals 0. And then we automatically get the Pythagorean theorem for vectors. If vectors u and v are orthogonal, then the norm squared of u plus v equals the norm squared of u plus the norm squared of v. We're going to use orthogonality to help us solve the fire engine problem. First, we have to identify some properties of orthogonality. If u is orthogonal to v, then u is orthogonal to any scalar multiple of v. And if u and v are both orthogonal to a third vector, w, then u plus v is orthogonal to w. Let's see the proofs. First, we show property O1. If u is orthogonal to v, then u is orthogonal to any scalar multiple of v. Okay, so we assume that u and v are orthogonal. What's the inner product of u with a scalar multiple alpha times v? The inner product can be rewritten as alpha times uv. We've just factored out an alpha. Now, the inner product of u with v is 0 because u and v are assumed to be orthogonal. So we have alpha times 0, which is 0. So that shows that the inner product of u with alpha v is 0, which shows that u and alpha v are orthogonal. Now, if u and v are both orthogonal to w, we want to show that u plus v is orthogonal to w. So what's the inner product of u plus v with w? Well, we can use a property of inner product to split up this inner product as the inner product of u with w plus the inner product of v with w. And each of these inner products is 0 because we've assumed that u is orthogonal to w and v is orthogonal to w. We get a sum of 0 plus 0 showing that this inner product is also 0. So u plus v is orthogonal to w. For example, the inner product, that is the dot product, of this vector u with this vector v is 0. So the inner product, the dot product, of u with 10 times this vector is also 0. Here's an example of the second property. We see that the inner product of this vector u with this vector w is 0, and that the inner product of this vector v with w is also 0. And we can combine these to get that the inner product of the sum of these two vectors with w is 0. And so the sum is orthogonal to w. Now we'll see how orthogonality can help solve the fire engine problem. We start with the vector B that represents the location of the burning house, and a vector A that gives us the line that the road goes along. So the line is the set of scalar multiples of the vector A. Now, let P be the point on that line such that B minus P is orthogonal to A. Then that's the point on the line that's closest to B. As an example, suppose the line is just the x-axis. That is the set of pairs xy such that y is equal to 0. And let the point B be B1, B2. So it looks like this. The lemma states that the point on the line that's closest to B is the point B1, 0. And let's see why that should be. For any other point Q, these 3 points form a triangle. Now, it's a right triangle because we chose P so that B minus P is orthogonal to this line. Since Q is different from P, the length of the base is non-zero. So by the Pythagorean theorem, the hypotenuse's length squared equals the sum of the square of the length of the height and the square of the length of the base. But since the length of the base is non-zero, that shows that the length of the hypotenuse squared is greater than the length of the height squared. That means that the distance from B to Q is greater than the distance from B to P. Let's see this in greater generality. Let Q be any point on the line. Now the points Q, P, and B form this triangle. Now P and Q are both on the line, so they're both multiples of A. So their difference, P minus Q, is also a multiple of A. Now, B minus P is orthogonal to A. Therefore, it's orthogonal to P minus Q, which is a multiple of A. That's using one of the properties of orthogonality we proved earlier. So, by the Pythagorean theorem, the length squared of the hypotenuse, that is, the length of B minus Q squared, equals the sum of the squares of the length of B minus P and P minus Q. If Q is not equal to P, then the length of the base is non-zero, which shows that the length of the hypotenuse is greater than the length of the height, which shows that B is farther from Q than it is from P. So the lemma states that among all the points on the line, the closest point to B is the point on the line such that B minus P is orthogonal to A. Now to simplify all this, we introduce a new definition. For any vector B and any vector A, we define two vectors. I call this one B parallel to A and this one B perpendicular to A. These are called the projection of B onto span of A, or the projection of B along A, and the projection of B orthogonal to A. And the defining equations are this. B has to be the sum of B parallel and B perpendicular. And there has to be a scalar sigma such that B parallel is sigma times A. And finally, B perpendicular has to be orthogonal to A. So you should think of this as breaking B up into a sum of two parts, B parallel and B perpendicular, satisfying these properties. Another way of stating the fire engine lemma is this. For any vector B and vector A over the reals, the point in the span of A that is closest to B is the projection of B onto span of A. And the distance between that point and B is the norm of B perpendicular, the norm of the projection of B orthogonal to A. Let's look at a simple example of this. What if A is the 0 vector? If A is the 0 vector, then the only vector B parallel to A satisfying this equation is the 0 vector as well. No matter what you multiply the 0 vector by, you're still going to get the 0 vector. Now, according to the first equation, if B parallel to A is the 0 vector, then B perpendicular to A must be equal to B. But that satisfies this third equation, that is, B perpendicular is orthogonal to A, because after all, A is the 0 vector. So every vector has an inner product of 0 with the 0 vector. Every vector is orthogonal to the 0 vector. Now, what's the point in span of the 0 vector that's closest to B? Well, the span of the 0 vector contains only one point, namely the 0 vector itself. So that has got to be the closest point. And the distance is the norm of B perpendicular. Well, in that case, that's the norm of B itself. All right. We're going to try to figure out how to compute B parallel and B perpendicular. These are the three equations that have to be satisfied by these vectors. We've already seen that if A is the 0 vector, then B parallel is also the 0 vector. So let's consider the case where A is not the 0 vector. We need to find the sigma for which B parallel equals sigma times A. By the third equation, B perpendicular to A has to be orthogonal to A. Therefore, the inner product of B perpendicular with A must be 0. Now let's substitute for B perpendicular using this equation. B perpendicular is just B minus B parallel. So we require that B minus B parallel have an inner product with A of 0. Now we use this equation to substitute for B parallel. The inner product of B minus sigma times A with A must be 0. Using homogeneity of inner product, this equation is the same as this equation. The inner product of B with A minus sigma times the inner product of A with itself equals 0. And this gives us the value of sigma. Sigma is the ratio of the inner product of B with A to the inner product of A with itself. And in the special case where the norm of A is 1, the denominator, the inner product of A with itself, is 1. So sigma is the inner product of B with A. Now let's use the procedure project along to write the procedure project orthogonal 1 that takes vectors B and A and returns the projection of B orthogonal to A, B perpendicular. The solution is just to take B and subtract the projection of B along A. The quiz is to write Python code for project along BA, which is supposed to return the projection of B along A. Here's the first answer you might give. It returns sigma times A. There's a problem with this in the case when A is the 0 vector. In that case, we have a divide by 0. So the best answer looks like this. It returns a multiple of A, and that multiple sigma is either this ratio of inner products if A is not the 0 vector. But if it is the 0 vector, the coefficient is 0. Mathematically, the implementation of project along we've given is correct. However, because of floating point roundoff error, we have to make a change to this. Often the vector A will not be a truly 0 vector, but practically it will be 0. If the entries of A are tiny, the procedure should treat A as a 0 vector. In other words, sigma should be assigned 0 in that case, and the resulting vector should be the 0 vector. We'll consider A to be a 0 vector if its squared norm is no more than some tiny number, say 10 to the minus 20. So here's a revised version of the implementation of project-along. Now we return at last to the fire engine problem. We'll take the vector A to be the 6, 2, and the vector B is the location of the house 2, 4. The closest point on the line consisting of all scalar multiples of A is the point B parallel to A, which is sigma times A, where sigma is the ratio of the inner product of A with B to the inner product of A with itself. We calculate that. It turns out to be 1/2. Therefore, the point closest to B is 1/2 times the vector A, which is 3, 1. And the distance to B is the norm of the projection of B orthogonal to A, which turns out to be square root of 10, which is just under 3.5, the length of the fire hose. The house is saved. Now, this fire engine problem can be restated as finding the vector on the line that best approximates the given vector B. And by best approximates, we just mean the closest. But this notion of best approximation comes up again and again in linear algebra. In least squares, which is a fundamental data analysis technique, in image compression, in principal components analysis, and in something called latent semantic analysis. In the next part of the course, we'll address the problem of least squares. The fire engine problem can be stated in this way. Given a vector B and a vector A, find the vector in span of the set consisting just of A that's closest to B. Now, a natural generalization of this problem is as follows. Given a vector B and a bunch of vectors, A1 through AN, find the vector in span of the set consisting of A1 through AN closest to B. That's the next topic we study.